I hope you can see me and hear me. Good evening, good night, good morning, good afternoon to all of my continents today, including, of course, Australasia. You go first, Australia, Africa, Europe, Asia, North America, South America, Antarctica, as always, New Zealand, Madagascar. Now I'm naming some of the more specifics within these continents. Hawaii, Indonesia, all the countries, all of the continents. Hopefully, I didn't miss anybody. If you're here from a place that I haven't mentioned, that I haven't covered, Mars, if you're in Mars, um, Venus, hopefully not because of its poisonous atmosphere. Hello, Stephen. If you are coming from any of the spots that I haven't mentioned, please do uh, let me know and I will correct it and give you a shout out. Stephen says, hey, my friend. Hello, Stephen. How are you doing? How's everything going? So, I am going to be covering a little bit about the fabric of space and how it may or may not be possible to tear the fabric of space according to Einstein. And we will see what the string theorist Brian Greene talks about and says about this in his book, The Elegant Universe, tonight, which we will talk about together and I will be sharing with you. Steven says, calls out from Pluto. I'm good, not up for long though. That's fine. I am just going to be up for a little bit, not too long. We're not going to go super late, but we're going to be here for a little while. So maybe like an hour or so, maybe under an hour. But don't worry about staying up too late. We won't be here too long, too long, too long. So if you're seeing this, by the way, as a video upload later on, as a live replay later on, thank you so much indeed for being here, for watching the live. If you're here right now as part of the live stream, thank you so much for joining. Welcome, welcome. Hello, Diego. Diego Ojeda says, Hola, hablas español. Hello, how are you doing? How are you doing indeed? ¿Cómo estás? I don't speak a ton of Spanish, but I speak a little bit. Thank you for joining, everybody. Could you please join and could you please like the live? Welcome, welcome, welcome. Good evening, everybody. Thank you so much for joining. And please do like the live and get ready to hear some interesting facts about space. So I wanted to mention that some of the details of general relativity that we have covered on this channel are quite a few lives ago. So a while ago, it might have been, so de Chile. Are you from Chile, Diego? Is that what you're saying? Because if so, well, thank you so very much. And welcome to Chile. In fact, before I go too far into the live, let me check something on the live control room over here on my laptop to make sure all of the settings are set and that I share the live. So I wanted to mention that a while ago, it might have been a few months ago, probably, hi Ishan, hello Stephen, hello Diego, hello Ishan, how are you doing? Ishan, are you are you the same Ishan that I'm kind of remembering? I can't tell. I can't tell. But nonetheless, welcome and thank you for being here. So let's see. Let me set that to save. By the way, Windry, I have Grammarly on my laptop, but do not know much about it. So if you have Grammarly set up as part of your Google Chrome extension, so Stephen here has been writing a science fiction novel that sometimes we also mention and read a few pages from here and there. And Stephen is a member of this channel, which I also recommend everybody go ahead, feel free to become a member if you'd like to support in that way and also to get some more specific content. Are you a transformer because you're Optimus Fine? Well, I don't know what that Optimus Fine means, but thank you and welcome to the live. A transformer. Okay, I don't know. Ishan says, I'm doing well, ma'am. Thank you, thank you, thank you again for being here. So, to answer Stephen's question, because we also encourage book authors, book writers, book tubing and book talking here. It's basically also a book club. Oh my gosh, book club kind of vibe. In other words, book club. Um, so because this is also a book club, um, what I have Grammarly do is it's part of the extension on my Google Chrome. And when I'm writing anything online, like say a blog post or anything, it basically gives me suggestions for grammar corrections, and it also autocorrects a lot of the grammar problems is how that works. So Stephen, if you go and say start typing on Google Doc or something like that, for your book, I do believe, or say your email, then I do believe Grammarly should kick in and help you out with the grammar as part of the Google Chrome extension. Now, Grammarly, if you want to sponsor my lives, then you should definitely do that because I just said all this stuff about you. But at the moment, Grammarly is indeed not a sponsor. I simply use Grammarly. Tigerface, hello, how are you doing? I am currently not deaf, but hopefully you can hear me and see me all right. Hello, how are you? So if you can, if there's any issues with hearing me or seeing me, then do let me know. But other than that, please do like the live. Can we get 20 likes? Can we get 40 likes? That would be most amazing. Please do support the channel. Very much appreciate you. But I wanted to mention earlier that I keep getting, that I keep forgetting is that remember a few months ago, it might have been in the I'm sorry for interrupting you, ma'am. Oh, thank you. Thank you. Yes, indeed. Please be sorry. And um, my ADHD, if I have such a thing, certainly uh, kind of suffers. But I needed to do this clickety clack of some things. Can someone share the live? Um, proper and well spoken. That's what I was wondering. So I can go to Microsoft Word and Grammarly will edit there. Did not know how to save otherwise. Um, it might only work if you are sort of online. So it's part of the Google Chrome extension, right? So Google Chrome is your browser. So you're using it um, what do you mean? What am I looking at? Oh gosh, some red flags. Okay. As you're browsing the web, say, for example, if you go to your email from your browser, or if you go to Google Doc from your browser, and then you start typing, then Grammarly should be catching all of that and then making suggestions for you to make changes to your sentences and sentence structures and grammar and all of that. So it's an online Google Chrome browser extension, which helps you, okay? ADHD and IC. Okay. So Tiger Face, yes, I may have ADHD, and your comment is distracting me from your other comment. So I guess it cancels out, to be honest. Once I start talking about the physics, I get much more in the zone. And after that, doesn't matter what you say. But hopefully you'll be saying supportive things. And thank you everybody for being here. I've seen that. Love it. Okay, good. All right. So can someone share the live? I just ate some food and I'm still chewing parts of an olive, apparently. Uh, Finding more in there. And okay, I started a goal. Short-term memory loss. Okay, I started a goal. If anybody wants to do a super chat or become a member or like the live or share the live or tell all your neighbors about the live or tell multiple countries about the live or subscribe. Oh, good. Yes, like and subscribe. See, you're helping. I forgot to put that in the chat. Indeed, I forgot to put that in the chat. And where are my mods? Thanks for your help getting to do this. Hard for me to open up like this. Like and subscribe, everybody. And Stephen, I think it's time for you to get over your fears with opening up, because I think you're doing great and you just need to keep on keeping on and keep on writing and sharing, okay? Keep on publishing. Make you a mod. Goodness. Thanks, but no thanks. So, okay, now let's see. I wish that things were easier. What is this? Oh, 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 oh. I'm looking at all of these markers appear in the video editor after your stream ends. Oh my gosh. I have all these new buttons on my live control. There is Baji, and I didn't see these earlier. And this too is now slightly distracting, but yeah. OMG, cute cat. Steven, you need, oh gosh. I've gotten past my fears. I have you and others took things to help me open up. This is Baji the handsome cat behind me. Okay, now I'm gonna share the live. So yes, please do like, share, and subscribe. And feel free to do a super chat. Feel free to show your love in ways that can actually support the channel, my loves. Oh, that didn't work very well. What does Baji do for a living? I love Baji, Suji, and Fuji. Thank you. So, okay. Volume off. There. Everybody, thank you so much indeed for being here. I love that you're supporting us. If you could also share the live with your best friend or your enemy, whichever one you prefer, that would be amazing. Baji's settling down for his little nap because he likes my voice and he likes to nap behind me or around me when I'm speaking. Combat sports! Oh, yes, my physics professor. Thank you. Thank you for being here, my friends. Thank you so much. Okay, so now, without hopefully any further distractions that I cause myself, I will get started with tonight's topic, which is going to be touching upon general relativity. Now, I want to remind you that a few months ago, it might have been in the winter months, I am kind of remembering being curled up inside some blankets and being a little cold in this house when I told you about some of the mathematics of general relativity. Now, remember that when Einstein was developing general relativity for us, after, of course, he gave us the special theory of relativity, which deals in space-time being relative, the mass-energy equivalence, and whatnot, and also gave us things like time dilation, length contraction, all of that stuff that we know and love. But then it was generalized to include gravitation and to include accelerating frames of reference in general theory of relativity. And this was done, of course, by including and really developing a math for four space-time. So not just the three spatial dimensions, but also time was part of the fabric of this connected or together space-time. And gravitation was this curving of space-time, or a massive object with a lot of mass would curve space-time more than a less massive object, for example. So this type of description of the curving of space-time and gravitation being described as a curvature of space-time is the sort of, that's the flavor, that's the contribution of general relativity. So I will say that one thing to keep in mind about general relativity mathematics is that the geometry, or the sort of foundation of general relativity, is a little bit different than our usual geometry. When we go to primary school, say, I don't know exactly in which grades what is taught here in the American school system, because I went to India for my primary school until the age of 18. I was studying in India. So over there, I think geometry was started maybe in the 5th or 6th grade. But basically, the geometry that we generally speaking learn in school is this Euclidean geometry. Okay, so this is where general relativity is a little bit different from geometry that we might be familiar with. And I wanted to make a note of that tonight, because this might be something that you might want to kind of look into. But also, several lives ago, probably in the month of November or December of last year, we actually went through some of the math of general relativity, including kind of defining out the metric, the geodesic, and those types of concepts, which really help you to understand some of the setup that's needed in general relativity. But I have something opened up here, taking the help of some AI actually, which will now tell us the difference between Euclidean geometry and Riemannian geometry. So general relativity is based upon Riemannian geometry. And this helps us to kind of define this sort of curving space-time and to do geometry with more than just 3 spatial dimensions or 2 spatial dimensions. Now remember that geometry, when we learn it in school as kids, that's generally, at first, it's just plain geometry, as in plain Euclidean 2-dimensional geometry. So where you can take a piece of paper and you can draw, whatever shapes a triangle is on the plane of a piece of paper, right? So it's a 2-dimensional object, basically. So a triangle, a square, a trapezoid. See, I'm just naming some of the geometrical sort of figures that people might be familiar with, and these are all 2-dimensional. So all of the geometry that we have learned that has to do with a square, a rectangle, a triangle, a trapezoid, name something else in the chat if there is a special geometrical object or figure that you would like to mention that you think is special that I did not mention here. Rhombus, I remember from school. These are all 2-dimensional. So all of the stuff that kind of fits on a piece of paper without having to curve it or do anything more or utilize the 3rd dimension is just 2-dimensional planar geometry. Then you can have Euclidean geometry also take up 3 dimensions. And once again, this is the 3 spatial dimensions generally that we live in. So remember, we've also talked about the spatial dimensions that we experience. And these are, of course, the length, the breadth, the height, the X, Y, Z sometimes we like to call, right? Our dimensions that we experience, extended objects, us, we are all 3-dimensional. So even if you wanted to do 3-dimensional kind of mathematics or geometry, Euclidean geometry will come in handy, and that is the one that we generally learn. Now, there is also Riemannian geometry, and this is spelled as R-I-E-M-A-N-N. Riemann is the person, and then Riemann, I believe it's a person. Please do double check. Riemannian geometry is, again, it's the R-I-E-M-A-N-N-I-A-N. So Riemannian geometry, it's different, and it accommodates more dimensions. Now, why was this necessary? It's because already in general theory of relativity, we are dealing with 4 spacetime. So actually, there are 4 dimensions in general relativity that he wanted to do the math with, the geometry with. So spacetime together with the 1 dimension coming from time and the 3 dimensions coming from space, 3 spatial dimensions and 1 time dimension, together actually form the 4 space-time dimensional geometry in general relativity. So you cannot do the typical Euclidean 3D geometry. You need something to be able to do the 4D geometry. So here, let me read to you what is the difference really between Euclidean geometry and Riemannian geometry. Hello, Crazy Sick One. Hello, 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 my dear. So Euclidean geometry deals with flat two-dimensional or three-dimensional spaces, while Riemannian geometry describes curved spaces, which can have any number of dimensions. So once again, it's nice because Riemannian geometry can actually accommodate even more than the four space-time that Einstein worked with. Now, Einstein was a very intuitive guy. He liked to, whatever he worked on, he liked to solve a real-world problem that we can sort of connect with, that he could connect with his intuition. So he actually kept general relativity to be totally kind of very rooted in reality as we experience it, because it was for space-time. So even though the math was kind of different, accommodating a four space-time or a four-dimensional kind of geometry, but actually we do experience the dimension of time, and we do experience the three extended dimensions of space. So in that sense, it was very much anchored in our real experiences when it comes to general theory of relativity. So, but I will say that Riemannian geometry can allow more dimensions. But in his case, he just used the four dimensions. Okay, so Riemannian geometry is the one that you need if you are going to do math or going to do geometry with curved spaces, including or involving many more dimensions, or just even one or two more dimensions. Even the one more dimension, which is the case with Einstein, four dimension, including time, would mean Riemannian geometry. Okay, and then there are certain things like the geodesic, the metric. Remember in that live where we set up all this math a while ago. So if you missed that live, that's okay. But it was several months ago we set it up. Oh my gosh, I think Siri has started to talk to me. Never mind, Siri. So a while ago, we set up this math, and we especially we defined a few of the specific things. So for example, sort of like a length, x squared plus y squared plus z squared. Take a square root of that is going to give you sort of the distance between two objects, right? There is an equivalent of this when you have four space-time dimensions, and when you do this with Riemannian geometry, like in general relativity. In that case, we actually have a different kind of definition for the similar thing, which is the square root of x squared plus y squared plus z squared, for example, in general relativity. And we kind of gave the definitions for all of that in that particular live a while ago. We might have called it, I think I called it Einstein equations or something like that. And because they are the Einstein equations, so Einstein literally had to start with those equations and take the help of Riemannian geometry and take the help of some of his mathematician friends in order to set up the math for general relativity. Okay. So once again, Riemannian geometry includes Euclidean geometry as a special case, of course, because Euclidean geometry is either 2D or 3D. But basically, Euclidean geometry is only useful when the space is flat. If the space has curvature, more dimensions, then you need the Riemannian geometry, okay? So Euclidean geometry, it's a system of geometry based on axioms and theorems that define relationships between points, lines, and figures in a flat, two-dimensional or three-dimensional space. This is why I started with the examples of the triangle, the planar geometry, squares, rhombus, trapezoids, what have you, rectangles. Those are all can be drawn on a piece of paper, which is two-dimensional. Or if you go to three dimensions as well, you get certain rules of geometry that you have to follow when you do Euclidean geometry. Parallel lines never intersect in the Euclidean geometry, as you, I'm sure, know. This is generally taught in school in the math classes. The sum of angles in a triangle is always two right angles. Who can tell me how many angles that is? 180 degrees. Thank you so much. Thank you so much for joining and subscribing. It's the familiar geometry we encounter in everyday life. This is the Euclidean geometry. Riemannian geometry. Now, coming to the Riemannian geometry. This is quite different from Euclidean geometry, okay? It generalizes Euclidean geometry to include curved spaces. So instead of just the flat stuff, now we can have curved spaces. It allows for spaces with varying curvature, including both positively curved, like a sphere, and negatively curved spaces. The concept of parallel lines is different in Riemannian geometry, as lines can converge or diverge depending on the curvature. So how two lines kind of meet or don't meet, the parallel stuff, this is quite different in Riemannian geometry, okay? It's going to be a little bit different. It's not going to be your intuitive stuff that you might learn or remember from primary school. So just keep that in mind if you're trying to understand Riemannian geometry, or if you're trying to kind of close the dots between the geometry we understand and general relativity, and some of the sort of concepts that we have to start with in general relativity, such as that metric and geodesic that I've been mentioning, okay? Riemannian geometry is essential in understanding concepts like space-time curvature in general relativity. Absolutely. Euclidean. So once again, Euclidean geometry assumes a flat space with zero curvature, while Riemannian geometry allows for spaces with non-zero curvature. So if you have a zero curvature, then it's a specific case of Riemannian geometry, which is basically the geometry we understand quite well, Euclidean geometry, which is a flat space, okay? So this I wanted to point out. We might not go into all of the details of the equations for general relativity today's live, but I wanted to point out this particular difference between the geometry that we learn in primary school, which is the Euclidean geometry, versus Riemannian geometry, because it is important in general relativity. And if you are interested in the topic, you can always go look it up yourself and kind of save some time during this live, because we will probably not be writing out all of these equations and things like that on this exact night. But we actually did show and write down some equations on a different live a while ago. It was called Einstein's equations. And you can imagine that this type of Riemannian geometry will allow you to write things down, which are sort of the equivalent, like I was saying about, of that distance, for example, distance between two objects. That's, for example, going to be written down in a different way. It's going to be similar. So it's if you kind of follow the Euclidean parallel path, then it's not too alien, Riemannian geometry. And once you understand that we just need to define out certain things using the four space-time, then it's actually really not that bad. And once you kind of get familiar with that setup in general relativity, it actually becomes a lot easier to follow, okay? Mathematically, that is. So for the people who like to understand things mathematically and to understand things geometrically and be able to write things down sort of in algebra, this is a very important step, okay? So now, with that out of the way, we will go back to this story and no more math, not too much math today for you. We will just read the book and look at what Brian Greene has to say. So this is going to be the book called The Elegant Universe, Superstrings, Hidden Dimensions, and the Quest for the Ultimate Theory by Brian Greene. So this is going to be mainly a string theory approach. So this book, of course, written by a string theorist, and of course, we've talked about superstring theory quite a bit. We've talked about supersymmetry, and we've talked about how really string theory is a grand unified theory candidate. It's trying to grand unify the two parts of physics mainly that are currently not unified, which is, or that were not unified. It's still not considered to be super unified because string theory is not testable. So we also talked about that, how string theory is not testable, how string theory requires these extra dimensions. So good thing that we just now mentioned the Riemannian geometry, which allows general relativity to be four-dimensional, because remember how string theory is actually 10 or 11 dimensional, depending on which iteration of string theory you're talking about. So the general sort of string theory that we have talked about so far has the 10 dimensions, where there are 9 spatial dimensions. So even though we experience the 3, normally we experience the three spatial dimensions. Those are the extended, experienced by us 3 spatial dimensions, the same ones as the ones I just mentioned, X, Y, Z. But then string theory is actually proposing and requiring 6 more curled up, very tiny extra dimensions that it requires in order for its math to work out and give us the grand unification of gravitation with quantum mechanics. And there are some other details too that I'm kind of skipping over at the moment. For example, it also kind of requires supersymmetry actually, And that's why it's called superstring theory. So where the super word comes from supersymmetry. So it's really superstring theory is really supersymmetric string theory, and also kind of inside of it requires supersymmetry, which very quickly is this requirement that all the particles have a supersymmetric superpartner particle. So for example, the leptons will have a superpartner called the slepton. Once these particles, these extra superpartner particles are discovered, we can say with a lot more confidence, both figuratively as well as mathematically, I mean confidence, that these are real. But until such discoveries are made, it will be a theory. And also superstring theory, because it requires these extra dimensions, is hard to test. Indeed, it has been so far kind of impossible to test out string theory, especially because its extra dimensions are very tiny, not probable by us at the scales that we're able to probe with our current technology. So these things are challenges of string theory, and we've been kind of discussing these. In which dimensions are the aliens from? Well, so it depends which aliens you're talking about. Superstring theory is 10-dimensional. There is a different evolution of superstring theory, which has 11 dimensions, but generally speaking, superstring theory has the 9 spatial dimensions and 1 time dimension. So altogether 10 dimensions only. But then there's another superstring theory, which is an evolved form of the superstring theory called M theory, which has 11 dimensions, because this one has 10 spatial dimensions. And these extra spatial dimensions is what really makes superstring theory or string theory unique. And it's not just a casual suggestion of string theory to have these extra dimensions. It's a requirement of string theory to have these extra dimensions. Without them, it doesn't really work. And the issue is that there is not an intuitive way to explain these 9 spatial dimensions, or the 6 extra dimensions, or in the case of M theory, the 7 extra dimensions. So that's sort of the issue, if you will, that we must face and sort of digest at the current moment. But string theory is also evolving. It's not considered to be a done theory. So of course, maybe there will be better explanations or intuitions coming forth. But at the moment, as far as I understand, string theory is not testable. Okay? So now I wanted to mention that all this things I just said about the Riemannian geometry, of course, it applies to string theory as well, because Einstein did 4-dimensional general theory of relativity. Remember that structure utilizing Riemannian geometry actually opened up the world of more dimensions to the people who came after. So string theory doing this thing with the extra dimensions, basically proposing or requiring the extra dimensions and finding a way to explain things with those extra dimensions, is only possible because of Riemannian geometry. So you have to keep this in mind. And if you want to understand this topic in more detail, then please do familiarize yourself with Riemannian geometry. Okay? And of course, again, general relativity only uses 4 dimensions, including time, and already needs Riemannian geometry. If you have more dimensions, even more, 4-dimension, 5-dimension, 6-dimension, in the case of string theory, superstring theory, it's either 10 or 11 dimension, then of course you would need the Riemannian geometry. Okay? Hi, Mr. Ayub. Hi, Jeep. Hi, Steven. Hi, Tiger Face. Hi, KK. Hi, XNT. Yes, please, you can feel free to watch this again. So somebody said that they might have to watch this a couple of times. Feel free, this will definitely post as a live replay video or a video upload later on under the live tab of the channel. So feel free to go and check it out and look at it again, or watch it again, or hear it again in the background as you do other things later on. And Riemannian geometry is spelled as Riemannian, Riemannian geometry. Okay, so it's pronounced a little different than it's spelled. So keep this in mind with the discussion we're about to have, because we're going to be talking about the tearing of the fabric of space. And again, we are talking about this Riemannian geometry type of space, okay? If you relentlessly stretch a rubber membrane, sooner or later it will tear. So sometimes you will find that in string theory, often we make certain analogies. We give some analogous sort of examples to kind of explain something. But but remember that our intuition is not very good for 10 dimensions or 11 dimensions. And so that we have to kind of sometimes make use of an analogy, but that analogy might not be so perfect in the end, because ultimately in string theory, we're talking about 10 or 11 dimensions and we live in 4. In Euclidean space, we live in 3. But if you want to include time, we live in only 4 dimensions. So it's very difficult for us to just casually understand the 10 or 11 dimensions. I thought you were saying Romanian geometry. No. Riemannian geometry. I thought string theory is about atoms and components. Is that true? String theory is about the unification of general theory of relativity, which describes gravitation, and quantum mechanics. So yes, to some extent it has to do with atoms, for sure. It tries to give a more general explanation of the particles, for example. So first of all, string theory has to subsume general relativity. General relativity is the updated theory for gravitation. We need general theory of relativity to understand gravitation more broadly and more accurately. So we had Newtonian mechanics. Are you a physics major? Yes, physics is my background. I have a PhD in physics. And all my degrees, actually, the ones I finished anyway, are all in physics. Okay? So basically, we had Newton give us a description for gravitation, but the updated theory for gravitation is general relativity. On the other hand, we also have quantum mechanics that developed largely in the 20th century, in the 1900s, if you will, hydrogen atom, Schrodinger's equation, all of that stuff happened in the 20th century. But these two sides of physics, quantum mechanics and general relativity, were not unified. They did not have a broader sort of umbrella theory that can subsume both of these parts of physics. So string theory is a grand unification candidate, a candidate theory. So I say candidate theory, not confirmed theory. I will tell you why, but it's a candidate theory for the unification of general relativity and quantum mechanics, because these two needed an umbrella theory, people thought, to sort of explain what is going on. Okay, with both of these sides of physics. I say candidate theory again because string theory is not testable. Okay. And that's why I love you. Oh, thank you. Baji's behind me. Thank you so much, everybody. So once again, we will see what Brian Greene has to say here, and we will hear a little bit about general relativity. And keep in mind about the Riemannian geometry. Once again, it is Riemannian, Riemannian geometry. This is what's used to describe curved space rather than flat space, okay? Because remember, in flat space, parallel lines never meet. But in curved space, parallel lines may meet. This is curved space. So curved space versus flat space. We don't actually live in a flat space. If you want to take into account more accuracy and describe this universe with general relativity, okay? If you just care about Newtonian mechanics or classical mechanics, like what we used to do a while ago, even now, actually, we do it. Even now, NASA still uses Newtonian mechanics to launch rockets and stuff like that. But if you want more precision, more accuracy, then gravitation is described as a curving of space-time, and that is that is formalized with Riemannian geometry, where space-time or space can be curved rather than flat. Okay? Relativity in quantum mechanics, you see, trying to remember that. Yes, the trying to unify relativity and quantum mechanics is the job of string theory. That's why it's a grand unification theory candidate. Candidate only because still called a candidate, not a confirmed theory, because it's not testable. Otherwise, it would be a confirmed theory. It requires all those extra dimensions. That's why it makes it impossible with the current technology to test it out, okay? If you relentlessly stretch a rubber membrane, sooner or later, it will tear. This simple fact has inspired numerous physicists over the years to ask whether the same might be true of the spatial fabric making up the universe. So we're getting into this tearing of the fabric of space discussion. This is why I wanted to first start with that Riemannian geometry discussion. Okay, this is the space that we're trying to maybe tear here. It's that curved space. That is, can the fabric of space rip apart, or is this merely a misguided notion that arises from taking the rubber membrane analogy too seriously? By the way, we will also mention wormholes in this chapter. Okay, so stay tuned for that as well. Einstein's general relativity says no, the fabric of space cannot tear. The equations of general relativity are firmly rooted in Riemannian geometry. And as we noted in the preceding chapter, this is a framework that analyzes distortions in the distance relations between nearby locations in space. In order to speak meaningfully about these distance relations, the underlying mathematical formalism requires that the substrate of space is smooth, a term with a technical mathematical meaning, but whose everyday usage captures its essence. No creases, no punctures, no separate pieces stuck together, and no tears. So this is basically saying that he roots his Einstein roots his equations of general relativity in Riemannian geometry. There are standard geometry equations that he starts with. It's actually very simple. So Einstein did not like to overcomplicate people's lives and physics and things like that. He was very simple, like four-dimensional space-time, where one of the dimensions is time, the three are spatial time. So it's not your plane geometry, it's not Euclidean geometry, but it's a very simple Riemannian geometry. There's nothing alien going on. Somebody actually mentioned about aliens. There's no aliens in general relativity. Einstein was actually mathematically a pretty simple guy. Okay, so were the fabric of space to develop such irregularities, so he didn't think that these types of irregularities were allowed. Okay, were the fabric of space to develop such irregularities, the equations of general relativity would break down, signaling some or other variety of cosmic catastrophe, a disastrous outcome that our apparently well-behaved universe avoids. This has not kept imaginative theorists. So by the way, wormholes, of course, appeared at first. Actually, I forget whether it appeared first in a fiction or not. It might have. But basically, the topics of that we discuss right now or going forward here is equally of interest in science as well as science fiction. So this is where science and science fiction can sometimes kind of overlap, okay? This has not kept imaginative theorists over the years from pondering the possibility that a new formulation of physics that goes beyond Einstein's classical theory and incorporates quantum physics might show that rips, tears, and mergers of the spatial fabric can occur. It's true, he did get a lot of help from mathematicians. It would be very difficult without that. It's true. He's much more of a physics guy than he's a math guy. But I mean, he's good at math, but for sure, yeah. I think you're right. I forget. I sometimes forget all the names of the people that helped him, but for sure. So we will see if there is any ripping or tearing of space that's allowed. Not so in classical theory of space-time, not so in general relativity. So remember that general relativity is an update to Newtonian mechanics as far as gravitation. So sometimes I say Newtonian mechanics and I say classical mechanics, and I mean the same thing, but I should sort of correct it in the sense that general theory of relativity is actually also a classical theory, in the sense that it's not a quantum theory. So there is classical physics and then there's quantum physics, right? Classical physics is generally the physics of the scales that we understand, that we experience, and quantum physics is the physics of the very small, subatomic scales, very tiny scales that are difficult for us to comprehend. Now, Newtonian mechanics is the old classical mechanics, and general theory of relativity is the new classical physics, which describes gravitation. So it's not to be confused with quantum mechanics. Quantum mechanics is another whole world. Remember how this quantum world and general relativity did not agree, is why there had to be Oh, thank you. These two, quantum world and general theory of relativity, do not agree, is why we needed a grand unification theory candidate to begin with, right? So, general relativity is classical, so it might not allow certain things, certain ripping, certain weird things, certain bizarre things that may be allowed in a quantum world. We will see. We will see what this has to say about that. But basically, string theory is trying to marry these two sides of physics, right? It's trying to marry the classical side with the quantum side. The general relativity side is the classical side. It's the new understanding of gravitation, but it's still a classical understanding of gravitation. And then quantum mechanics is the other side, which has nothing, no unification with this side. They're two fragmented parts of physics. And quantum mechanics is saying, well, we can describe the physics of the very small, and we're happy with that. Whether we seem bizarre or not to classical people, we don't care because we have experimental success, and they do. Remember, all of particle physics came out of quantum mechanics, and if particle physics was not experimentally successful, then it would have been killed long ago, right? So all of those particles being discovered, all of the particle properties being discovered, all the quantum mechanical properties being discovered, like mass and charge and spin and color, all of that means that quantum mechanics is successful, and you have to include it in your more general theory. And so string theory does. So string theory is actually somebody who is actually a theory that is going to include quantum mechanics. So you can expect some quantum stuff to happen in string theory. It's not like, oh, because it's not allowed in general relativity, string theory cannot handle it, right? String theory should be able to more than handle it. String theory should be able to handle general relativity, quantum mechanics, and more, not less, right? As a grand unification theory candidate. So let's see what the string theorists have to say about the tearing of space. In fact, the realization that quantum physics leads to violent short-distance undulations led some to speculate that rips and tears might be a commonplace microscopic feature of the spatial fabric. So the thing that Einstein said was not allowed, which is to rip the space-time fabric, maybe, who knows, may just be allowed in quantum. The concept of wormholes, so here we go. Some people really like wormholes, so here you go. The concept of wormholes, a notion with which any fan of Star Trek, who is a fan of Star Trek here? Deep Space Nine is familiar, makes use of such musings. The idea is simple. Imagine you're the CEO of a major corporation with headquarters on the 90th floor of one of New York City's World Trade Center towers. Well, I guess this book may be a little old. Oh gosh. I'm so sorry. Trigger warning about those towers. Through the vagaries of corporate history, an arm of your company with which you need to have ever increasing contact is esconded on the 90th floor of the other tower. As it is impractical to move either office, you come up with a natural suggestion: build a bridge from one office to the other, connecting the two towers. This allows employees to move freely between the offices without having to go down and then up 90 floors. So wormholes, in a sense, is sort of this connection between two parts of space-time, which is sort of like a little shortcut, but it does require some shenanigan to happen, it does require some rules to be broken. See, classical physics, classical theorists, classical theories like Newtonian mechanics, general relativity, don't like the rules being broken. They're very rigid in that sense. Quantum mechanics, on the other hand, is probabilistic, uncertain, and it's almost like the rules are meant to be broken in quantum mechanics. So if there's anything, any rule that you really love, it may just be getting broken in quantum mechanics, and we can probably just explain it away by saying, oh, there were quantum fluctuations. Some pairs of stuff did something, and one of them did the other thing, and maybe it's possible. Almost anything is possible when you consider it as a quantum effect, okay? A wormhole plays a similar role. So we were trying to give you an analogy for wormhole with that tower example. It's a bridge or tunnel that provides a shortcut from one region of the universe to another using a two-dimensional model. Imagine that a universe is shaped as, here's the little picture. If you can see, here's the book and here's the picture. Let me show you. That shows you a little bit of the picture. I'll show it to you again later. But if you if your corporate headquarters are located near the lower circle, there's this circle example of, see how in this circle example, it's actually kind of showing you a curved surface. And if there is a way to join together 2 points on this surface in a shortcut kind of way, that would be sort of a wormhole. But see how even this example kind of uses that curvature. So anyway, if your corporate headquarters are located near the lower circle, you can get to your field office located near the upper circle only by traversing the entire U-shaped path, taking you from one end of the universe to another. But if the fabric of space can tear, developing punctures, as in the case where you develop punctures and could maybe go through, and if these punctures can grow tentacles that merge together, a spatial bridge would connect the previously remote regions. This is a wormhole, and I'll show you the picture once again at the in a little bit. You should note that the wormhole has some similarity to the World Trade Center bridge. Oh gosh. But there is one essential difference. The World Trade Center bridge would traverse a region of existing space, the space between the two towers. So just an analogy, the tower example, okay? On the contrary, the wormhole creates a new region of space, since the curved two-dimensional space is all there is. So wormhole, in other words, is sort of this creation of a new region of space, a little tearing of the fabric of space-time, and then also sort of a new thing that's happening to connect those two parts of the universe, which would otherwise be unconnected, disconnected. So two parts of the universe, because of curvature, being disconnected completely, being connected with a wormhole, which kind of tears the space-time fabric and then makes a new connection. That's a wormhole. Okay. Regions lying off of the membrane merely reflect the inadequacy of the illustration, which depicts the U-shaped universe as if it were an object within our higher dimensional universe. Thank you. The wormhole creates new space and therefore blazes a new spatial territory. Do wormholes exist in the universe? Right? That's a big question. Wormhole, H-O-L-E, gosh. So do wormholes exist in the universe? No one knows. And if they do, it is far from clear whether they would take on only a microscopic form or if they could span vast regions of the universe, as in Deep Space Nine. But one essential element in assessing whether they are fact or fiction is determining whether or not the fabric of space can tear. So it's almost like, so we actually talked about this when we read The Brief History of Time by Stephen Hawking. So remember how we basically said that particles kind of time travel already. So this whole situation of wormholes and time travel is something that we talked about in great detail, referenced in the book A Brief History of Time and a couple other books too at various points in this live. So in previous lives, so if you've missed our Stephen Hawking and other like Einstein's Cosmos, Michio Kaku type of lives in the past, then I highly recommend go find those, because we talked about this already. And we kind of said that actually, remember those two parallel metal plates example of trying to make time travel happen? Remember? That is actually like a sound way of doing time travel, and by sound I mean it's an okay, like it's an allowed way of doing time travel. You could do it. It's actually tested that you can actually create negative energy density in between those metal plates, and you can basically use it to create such a thing, such a time travel machine type of thing. But the only problem was that our technology was not at this point advanced enough to sustainably make such a device and to kind of do time travel at the macroscopic levels. So we talked about this time travel business. We also talked about the arrow of time, what it really means, in which way is time flowing. There's the cosmological time, there's the thermodynamic time, there's a psychological time. There's like 3 definitions of time, by the way. And they all kind of are uh, quite consistent, thank goodness. Otherwise, I mean, we would be going a little stir crazy. But remember how cosmological time is the time, is the direction of time in which the universe is expanding. So if you are going along a time in which the universe is contracting, then you might be going backwards in time. So you might be the character of like that show or movie Back to the Future. If it looks like the universe is contracting all around you, then please do something, because I think you're going backwards in time. The other way is the second law of thermodynamics gives us that entropy always increases in the universe. So the time along which the time direction along which the entropy of the universe increases is the correct and forward direction of time. That's the other way to think about the direction of time. And lastly, we have psychologically a direction of time. We have some memory. We have a certain psychology associated with time where we remember the past and not the future. Now, some people in divination, some people who may have special spiritual divine skills, I'm not sure, but it is possible that they could remember the future, right? There are people like that, but generally speaking, normally, as far as we know in psychology, we only remember the past and not the future. And so, for example, the cup of tea example, where the cup of tea, once it spills and breaks on the floor, and there it is on the floor in the pieces, for example, you associate that as the forward direction of time, like where you remember, oh yeah, the cup of tea was there, it was in one piece, and now it's broken, it's in all these shattered pieces. You don't necessarily remember the shattered pieces first and then you know what I mean? I think you get it. Basically, there are the 3 ways of understanding the direction of time. There is the cosmological time, which has to do with the expansion of the universe, the thermodynamic time, which has to do with the entropy of the universe always increasing and only increasing. And then there is the psychological arrow of time, which has to do with how we remember things. And if you remember things differently, then you might be quite special, but those are the ways. So it is not so bizarre to do time travel, actually, at the microscopic scales. So we kind of talked about this already, that actually particles kind of sort of do time travel already. So at the microscopic scales, at the quantum scales, we've seen Feynman diagrams where the particle antiparticle, like basically the particle going forwards in time is sort of equivalent to the antiparticle going backwards in time and things like that. So in the Feynman diagrams, pretty much time travel is allowed for particles. At microscopic scales, it's not such a bizarre thing. Now, is it allowed in classical mechanics? Is it allowed in classical theories? Is it allowed in general relativity? Is it allowed by Einstein? No. But in particle physics, in microscopic world, in quantum world, it may not be such a big deal after all, actually. Okay, so you have to, again, when we talk about time travel, if you are interested in time travel, if you're interested in wormholes, just keep in mind, it's about who you ask. And if you're interested in, say, for example, doing some time travel yourself, it is about the context and the, regardless of the technology development or not, whether it's allowed is quite different depending on the context. In the quantum mechanics or particle physics context, it may very well be allowed. In the classical context, it may very well be disallowed, or they might say that there is not a good geometry for it, okay? So keep in mind and keep an open mind to these types of things. But as far as do wormholes exist in the universe? Well, I guess we don't know. Black holes provide another compelling example in which the fabric of space is stretched to its limits. So this is the other topic that we've also spent quite a bit of time on. So black holes, remember, are another example of a physical object, of a topic that both has a classical theory and a quantum theory. So in classical theory, a black hole is a singularity. It is actually something that was predicted and totally, given to us by Einstein's equations, by general relativity, but it was considered to be a bizarre enough type of object where people were not expecting it to be real. They didn't think that we would actually find black holes or dark stars, or what, they called them dark stars or point stars or black holes, meaning that it's a singularity, it's a point of such infinite gravitational field density that even light cannot escape, right? Even the gravitational field of this thing is so high that it bends space-time in such a way that even light cannot escape. So, and in fact, that is how you set the equations of the black hole, and you find at what radius does the object become a black hole by setting it equal to the speed of light, to be the escape velocity from this object. And that's how you find the radius at which this massive object becomes a black hole, and it's called the Schwarzschild radius. So this is all stuff that we have kind of covered as well. So we've talked about black holes at length as well, especially because of course, Stephen Hawking worked on them. So that's the classical theory of black holes. People were, quite, how should I say it, quite shocked when black holes turned out to be very real. They are actually a part of nature. Black holes are a thing. Sometimes massive stars basically compress down or contract down or collapse down to a black hole when they die. If they're a massive enough star, it can very well happen. So that's a way in which we can get a black hole. So it's another example where classical theory and quantum theory will not totally agree, though, right? So this is the classical approach. Then there is the quantum approach, which actually ends up giving black holes a temperature. Point stars. Oh my gosh, point stars. POINT, a star that's a point light, a star that is a point. We're talking about astronomy, if that helps. So, so that's the classical theory of black holes, and in the quantum theory, it's much more of a diverse theory in where you can actually sometimes have things escaping a black hole, depending on sort of what's happening. But with quantum fluctuations, we actually see that particles can sometimes escape black holes, and that actually contributes to black hole radiation that actually gives black holes a temperature. So anyway, all of that was to say that wormholes may be a thing. Remember that the ripping of space-time is not really allowed in classical theory, but it may be a thing that could happen, maybe. Just like black holes had a classical theory, but then it was shown with more of a quantum approach that black holes may have a temperature. So, it's basically two types of approaches may give you a better, more whole picture, more complete picture of something, okay? Black holes provide another compelling example in which the fabric of space is stretched to its limits. We saw that the enormous gravitational field of a black hole results in such extreme curvature that the fabric of space appears to be pinched or punctured at the black hole's center. Unlike in the case of wormholes, there is strong experimental evidence supporting the existence of black holes. So the question of what really happens at their central point is one of science, not speculation. Once again, the equations of general relativity break down under such extreme conditions. So a black hole is an example of a singularity, for example, in the mathematics. Some physicists have suggested that there really is a puncture, but that we are protected from this cosmic singularity by the event horizon of the black hole, which prevents anything from escaping its gravitational grip. This reasoning led Roger Penrose of Oxford University to speculate on a cosmic censorship hypothesis that allows these kinds of spatial irregularities to occur only if they are deeply hidden from our view behind the shroud of an event horizon. On the other hand, prior to the discovery of string theory, some physicists surmised that a proper merger of quantum mechanics and general relativity would show that the apparent puncture of space is actually smoothed out, sewn up, so to speak, by quantum considerations. So basically, they're saying that maybe something of a ripping of space-time happens inside the black hole, but we can't see inside the black hole because light doesn't escape a black hole, classically speaking, anyways. And we are sort of limited to the event horizon of the black hole. Remember, the event horizon is where that is the point up to which we can observe. Whatever happens inside of the event horizon of a black hole, we don't know. So information does not travel out of the black hole. Again, classically speaking, outside of the event horizon, outside of the radius of at which lies the event horizon of a black hole. So if there is some interesting phenomenon, some weird shenanigan happening inside a black hole, which is sort of a ripping of space or a wormhole or some other thing, some whatever you would like to imagine, that could be happening inside a black hole, but we simply won't know because we don't know what happens inside a black hole. We have, so to speak, a cosmic censorship, as far as we understand so far, anyways, that prevents us from knowing what happens inside the black hole. We only know out from the event horizon onwards. Now, once again, though, this is a classical approach. Classically speaking, the black hole event horizon, nothing can really escape it. We saw that if you include quantum considerations, that is actually how you get a temperature for the black hole, you get Hawking radiation. This is what Stephen Hawking is famous for. So it's not that we haven't ever brought a quantum approach to the black hole. We have as a community, but generally speaking, we think of black holes as classical objects where even light cannot escape it. We cannot get the information out of a black hole. So even if there were things going on inside of a black hole, which has to do with wormholes or ripping of space or some other exciting thing like Star Trek type of thing, or Star Wars, I don't know. I actually don't watch science fiction all that much, but even if there was something happening, we wouldn't know. At least not yet, we don't know. But could there be a sort of merger of quantum mechanics with general relativity, such as string theory, that could maybe give us some better explanations and some more information? So this is sort of the idea, okay? Does our galaxy have a black hole? Yes, indeed, my love. So we have a supermassive black hole at the center of our galaxy. Yes, Sagittarius A star. So it's the pronunciation, the way it's written is Sagittarius A asterisk, and the way we pronounce it is Sagittarius A star is a supermassive black hole at the galactic center of our own galaxy. We're all rotating around it. We're all orbiting it. Our sun has gone around or done its orbit around the galactic center around 20 or 21 times. So in that sense, our sun is a sort of a 20-year-old in the galaxy. So actually, the rotation of matter around the galactic center of our own galaxy and sort of seeing the orbital velocities of things is actually how we, that's the direct evidence of dark matter in the galaxy, by the way. It's a very important question that you ask, and it's related to another very important topic, which is the topic of dark matter. So since the matter in our galaxy, us included, are orbiting the galactic center, which has this supermassive black hole, there is some observations to do with the orbital velocities of things that point to the fact that there's more matter in the galaxy than we can see. Okay? What could rip a black hole? Oh, wait. I don't know what you mean. I think the ripping inside of a black hole that we're talking about here has to do with the fact that it's a point of incredible gravitational field density. It's just this point of such big gravitational strength that you might imagine ripping the space-time fabric inside of a black hole, which we would not really know about because we won't see it from outside of the event horizon. If that's what you're asking, I'm not sure what you're asking. Do black holes absorb electromagnetic waves? Yes. Black holes bend space-time. Wormholes tunnel space-time. Yep. Some people are laughing, so I'm guessing this was something else, but whatever, I don't care. Tear the neutron star from the white dwarf. Yeah, Sagittarius A star. So it's written as Sagittarius A asterisk, but we say Sagittarius A star is the name of our galactic center supermassive black hole. Oh, another thing I should mention here really quickly is that the supermassive black hole at the center of our galaxy and other galaxies, a lot of galaxies have supermassive black holes at their center. They become big due to eating more stuff. Like they're constantly accreting a lot of material. The black hole at the center of our own galaxy is accreting a lot of material, as in a lot of extra material is constantly falling into it. And so it has eaten a lot over the years and it's become very, very big. So black hole is one of the, in general in astronomy, black hole is one of the stellar remnants. Okay, so when a star dies, it can either become a white dwarf or a neutron star or a black hole. I mentioned, or I see some people mentioning those, so I'll just say it really quickly. So depending on your mass, when you're a star and you run out of nuclear power, as in you're done kind of burning nuclear power in your belly and you've made all the elements that you could and you're sort of done, and gravitation is kind of winning over and you're about to collapse and you're going to die. After you die, you've done all kinds of things. There's a process, there's a supernova of some type. Once you die, you collapse into a more compact object. Now, this compact object can either be a white dwarf or a neutron star or a black hole, depending on the mass of the star. More massive the star, the more likely that it will be a neutron star or a black hole as the stellar remnant, okay? Because basically a neutron star or a black hole is a more extreme example of compression or collapse gravitationally for that star, okay? So that's what's going on. So for the most extreme cases of huge collapse of a huge star, you might imagine that it would collapse down to as extreme as a black hole. And that's where people were actually kind of hopeful that they might see black holes out in nature. And of course, now we have, is because they were like, oh, like if they can collapse down to a neutron star, because at first actually neutron stars were discovered. Neutron stars are like 10 kilometers radius. That's very small compared to the original massive star that would then collapse down to a neutron star. So once neutron stars were discovered, that was basically an indication that, oh my gosh, if this type of compression or collapse or contraction of a massive star is possible, and we're seeing it in nature, neutron stars, pulsars, generally they're pulsating stars usually. If that's possible, then maybe even black holes can be possible, because black hole is an even more extreme collapse or an even more extreme compression of a dying star, okay? Black holes will continue. So black holes generally accrete a lot of matter that's around them. So I don't know what you mean by electromagnetic. So electromagnetic waves, I mean, that's just light. So generally what happens is black holes will continue. If a black hole has become quite big, then it's likely that it will continue to accrete more and more matter into it, as in more and more matter will be falling into it from its neighbors. And that neighboring stuff that it's accreting matter from, that infalling matter will actually radiate a lot of energy. The matter that's infalling into the black hole actually undergoes very extreme acceleration and can produce certain types of radiation because of that. And that is some radiation that we can see in all kinds of wavelengths, sometimes X-rays or radio waves or whatever. We actually see this in our case, in the galaxy, in our own galaxy from our galactic center. So if you mean that, then yes, there is a lot of electromagnetic radiation generally around a black hole. So this might be what you're asking. um, okay, I'm not sure I follow. I have to come back to that. So basically, if you mean the electromagnetic wave around a black hole because of the infalling matter that is falling inside a black hole and creating a lot of and undergoing a lot of acceleration and basically giving off synchrotron radiation and things like that, then you're right. There is a lot of radiation that kind of actually surrounds a black hole in that sense, and will kind of render it very bright. So even though black hole itself, even light cannot escape it. So a black hole is dark, but around a black hole can sometimes be very bright because of the infalling matter, which undergoes acceleration, which undergoes then giving off a lot of radiation, electromagnetic radiation in various wavelengths. So that could be something that you might be wondering about. Black hole sounds like okay. No, it always goes. That's an interesting question. Doesn't usually matter goes out of a black hole as opposed to in. No, generally nothing can escape a black hole. Generally speaking, once you've fallen into a black hole, there is no coming out. Okay, there is no coming out. So this is why actually we don't think of, what was I going to say? Oh, I lost my train of thought. The CMB has energy, so a black hole will gain mass from it. I see. Yeah, like maybe photons will fall into a black hole, Hawking radiation. Is that what you were talking about? Yeah, maybe that was what I was talking about. So basically, I lost my train of thought because the comments are distracting. But generally, we don't consider. Oh, this is what I was saying. Generally, we don't consider. We don't say that we really know what can go on inside a black hole, because after the event horizon, nothing can come out. So the information cannot leave the black hole. But in the case of Hawking radiation, like someone is mentioning, there is a quantum, classically speaking, black holes, you cannot escape a black hole. Once you've crossed the event horizon, even light cannot escape a black hole. Once you've crossed the event horizon of a black hole, nothing can come out of that black hole, classically speaking. With quantum, you can actually explain through quantum fluctuations black holes emitting some level of some particles, which actually gives it a temperature, which actually gives it a radiation. So because if it's not emitting anything, then it doesn't have any radiation. If it doesn't have any radiation, it doesn't have a temperature. Event horizon. Oh, good. There's a movie called Event Horizon. I didn't know that. You are distracting so intelligence. I don't know what that means, but okay. I am distracting? I'm distracting from what? This would make a great movie on a script. Okay, you should watch the movie called Event Horizon. I didn't realize there was a movie called Event Horizon. Thank you for telling me. I would call the movie Interstellar. But yeah, I got distracted. I just wanted to mention one more time that classically, after the Event Horizon, nothing can come out of a black hole. But in quantum mechanics, there is a way that you can actually have a few particles escaping a black hole. It's generally part of a pair of particles. It could be the particle antiparticle pair. One of them kind of falls into the black hole. The other one escapes after sort of a particle divorce of sorts. And from that, you can actually have a black hole emitting things in quantum. And then that's how the black hole has radiation and it has a temperature. Okay. So what will win in the end, the black hole absorbing CMB or Hawking radiation? Oh, very nice. So I will give you a thermodynamic answer to that. Whatever increases the entropy of the universe, I think will win in the end. What do you think, Drew Crew? That's not true. It's the guy from the first Jurassic Park. Um, Spaghettification. Sure. So thank you so much. And please do like the live. So basically that is a great point. So somebody asked about the CMB photons. We know that there is this primordial cosmic microwave radiation photons that are still hanging out. And so black holes are probably going to absorb some of that. And black holes also give off a radiation. By the way, did you know that do I remember this correctly? The bigger black holes actually have a lower temperature. Is that right? Right? So anyways, um, I think any process that ends up happening, it's the one that's allowed, and that the one that will keep on happening is the one that increases the entropy of the universe. So I'll give you the second law of thermodynamics. Oh, Baji's right there. No entropy. It just keeps subscribe. We'll learn a lot from you. Thank you for subscribing. Thank you everybody for being here and for subscribing and all of that stuff. Still, spaghettification is to do with tides. So basically, around a black hole, you will feel a very intense gravitational field, and depending on how you say you want to really find out about the inside of a black hole, okay? In fact, we can talk about this formally from one of my other favorite books. So say you want to dive inside of a black hole to find out what is in it. And maybe you're very daring, and it's okay. You want to see what's inside of it no matter what, right? So depending on depending on depending on how you want to feel, you might want to choose a certain way of diving in. So basically, spaghettification is simply tidal forces that are felt by an extended body that might be approaching a black hole, depending on how you approach the black hole. So because there will be tidal forces across this extended body, there's this thing called spaghettification of the extended body that could happen near a black hole. But I have a very nice discussion here from this book called Foundations of Astrophysics by Barbara Ryden and Bradley M. Peterson, which actually talks about this very nicely. So let me pull that up. That's actually very helpful. Ooh, the spaghettification word might actually help to find the spot. Um, no. Tidal forces, maybe? What, this? No, this is a book. Is it to do with Sagittarius A star that she talked about that? I forget. I'm trying to get to the point in the book. Looking at the index here. Give me 1 second. So basically, there is a nice little discussion of how you can dive into a black hole with some strategy. So let's talk about that, because it's actually helps to understand it. 462 Sagittarius A star. I wonder if she will. Yes. This is it. Yeah. So whether you will be tidally shredded or not is something that we will discuss when you're going into a black hole. Okay. So the galactic center has this. We talked about it. There is some bright stuff going on from the galactic center. It's a strong radio source, Sagittarius A. They figured out that there is a black hole there. It's called Sagittarius A star. So in this book, they talk about Sagittarius A West and whatnot. And then if we zoom in on the center of Sagittarius A West, we find a highly compact radio source called Sagittarius A star. Once again, that's A with an asterisk, and we call it Sagittarius A star, meaning the supermassive black hole at the center of our galaxy, okay? The angular size of Sagittarius A star has been measured using radio interferometry at a wavelength lambda equal to 7 millimeters. The measured diameter of Sagittarius A star is around 0.8 milliarc second, okay? So that's quite small, corresponding to around 6 astronomical units in physical units, where our distance from the sun is, of course, 1 astronomical units. The high angular resolution provided by radio interferometry also enables a measurement of the proper motion of Sagittarius A star. Measurements reveal directed almost entirely along the plane, blah, blah, blah. Observations by the Chandra X-ray Observatory revealed that Sagittarius A star is an X-ray source as well as a radio source. So I was mentioning how the infalling matter into a black hole will sometimes give off a lot of different radiation in different electromagnetic wavelengths, such as in this case, X-ray, radio waves, etc. Right? The X-ray emission from Sagittarius A star varies significantly on timescales of less than an hour. Wow. Revealing that the majority of its X-ray emission must come from a region less than 1 light hour across, right? Because remember, we are, how many light minutes are we away from the sun, gentlemen and ladies? What is the distance of us from the sun in light years or light hours or light minutes? Somebody put it in the chat. Exactly. Very nice. 8 what? Exactly, 8 minutes. So it takes light 8 minutes to get to us. The variation of X-ray shenanigans with this Sagittarius A star was happening across 1 light hour, which means that that's sort of giving you an idea for the length of this thing. Okay, so let's review what we know about Sagittarius A star. It is a fairly luminous but highly compact source of radio and X-ray emission located at the galactic center. So whoever asked about the black hole, whether there is one at our galactic center or not, this is the answer to that. So there you go. The bolometric luminosity of Sagittarius A star is not exactly known due to the high extinction at many wavelengths, but is estimated to be around 1,000 solar luminosities, okay? The leading hypothesis is that Sagittarius A star is a supermassive black hole that is accreting gas. All of that accretion is making a lot of things fall in with some acceleration and giving off a ton of radiation, okay? A supermassive black hole is a black hole larger than would result from a massive star collapse alone. So this is what I was saying earlier. Stars can collapse to make either a white dwarf or a neutron star or a black hole, but a supermassive black hole is not just happening due to the collapse of a star. It's happening probably due to the collapse of a star long ago, and then after eating a bunch of stuff, it has accreted a lot of material onto it over the ages before it became a supermassive black hole. The black hole hypothesis is testable by looking at the motion of stars in the vicinity of Sagittarius A star. So Sagittarius A star, the black hole, you can look at how stars are sort of going around it. If there is a black hole present with mass m black hole much greater than a stellar mass, then stars on elliptical orbits around the black hole will obey Kepler's third law. Oh my God. So, uh, adaptive optics imaging at lambda around 2 microns has enabled astronomers to track a few bright stars near Sagittarius A star for more than a decade. So, blah, 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 blah. There's some more. Let me tell you. Let me tell you. Whoever asked about the black hole, guess what the mass of the black hole is? Guess what the mass of the supermassive black hole at the center of our galaxy is? It is 3.7 times 10 to the 6 solar masses. So 3.7 million solar masses. That is, solar mass is the mass of our own sun. So take the mass of our own sun, 3.7 million of that is the mass of the supermassive black hole at the center of our galaxy. Okay, so definitely we have a supermassive black hole here that we're all orbiting around, etc., etc. Okay, so now let's talk a little bit more about the tidal stuff. Higgs field, we can talk about that another time. Wedding DJ? No, it's fine. We can talk about the Higgs field some other time. Wouldn't it be great if this was the wedding music album that they're playing? So we learned that black holes less massive than 2,000 solar masses. So if a black hole is less than around 2,000 solar masses, ooh, oh, we can talk about this too. We can actually go back to this section later on. We learned that black holes that are less massive than 2,000 solar masses would tidally rip you apart before you could reach the event horizon. So it's actually how you dive into the black hole and also the mass of the black hole. So the mass of everything in astronomy is always very important. So depending on the mass of the black hole, if you dive into a black hole to see what's inside of it, depending on you might want to choose a more massive black hole because the tidal shredding will happen, I believe, more for a smaller mass black hole. Okay, so let's read this real quick, but I think now I've found the part that I was actually gonna find. It's in section 18.3. So we learned that black holes less massive than mass black hole around 2,000 solar masses would tidally rip you apart before you could reach the event horizon. So if you're getting tidally ripped before you have even reached the event horizon, that means you're already kind of dying and in a lot of pain by the time you've reached the event horizon. So you're not going to be in a very fit state to see inside the black hole. So the recommendation is, I believe, so double check this, is that if you want to see inside the black hole past the event horizon, you might want to pick a black hole that is more massive, okay? And the math of that is something we can cover. So if you wanted to dive into our galaxy's supermassive black hole, you wouldn't be tidally destroyed until after passing the event horizon, which is really nice. So you could dive into our galactic center's supermassive black hole and maybe not be tidally destroyed, which is quite nice. But what would happen to a star? Because your mass is being taken into account as well. And so if you dive in and it's a black hole with a lot more mass than 2,000 solar masses, then I guess you would not be ripped apart before you are inside. So maybe that's a great opportunity for somebody. But what would happen to a star approaching the black hole? Stars are held together by gravitational forces. Thus, a star of mass m star and radius r star would be tidally ripped apart at a distance of r rip from the black hole's singularity. The distance r rip is where the differential tidal force across the sky is where the differential tidal force across the star is equal to the gravitational force holding the two halves of the star together. So once you do this math of the differential force and the F gravity of the star, then you get a star similar to our sun, for instance, would be ripped apart at a distance of around 10 to the 8 kilometers times some more things, including involving the mass of the black hole, from a supermassive black hole. When we compare this to the Schwarzschild radius of the black hole, we find that sun-like stars would be ripped apart before entering the event horizon, so long as the mass of the black hole is less than 10 to the 8 solar masses. So if a star is swallowed whole by a black hole, it doesn't produce a major outburst of radiation before it enters the event horizon. So if as a star, it wants to be kind of quietly entering a black hole to be then swallowed whole and not cause a lot of radiation along the way, then a smaller black hole would be the way to go. But actually, for us to be observing such things happening, if we want to be sort of getting electromagnetic radiation signatures, for example, of black holes swallowing other things or stars and whatnot, we would actually want those radiation clues that something was swallowed or something was accreted. But if something gets swallowed whole, then we don't have those signatures of electromagnetic radiation from the accretion, okay? So we will actually read this again because we will talk about it from the correct section. I forgot that there was another section about this, but yeah, anyway. If a star is swallowed whole by a black hole, it doesn't produce a major outburst of radiation before it enters the event horizon. However, if the star is tidally shredded first, its gas forms a hot accretion disk around the star and produces copious emission as it spirals in toward the event horizon. Wow. Wow. So when a star is tidally shredded first, before it enters the event horizon, just like we could be tidally shredded first before we enter the event horizon. If some tidal shredding happens before we enter the event horizon or before some other star enters the event horizon of a black hole, then there will be immense acceleration of the infalling matter into the black hole, which will produce a lot of radiation. And that's actually how we on Earth, astronomers, can see such radiation around a black hole, and it's a giveaway for that black hole. It actually, sometimes it's funny that around a black hole can be kind of bright because of this exact reason, the accretion of the infalling matter. But if something is swallowed whole and not much acceleration or shredding or tidal shredding or spaghettification happens for the thing that's falling into the black hole, then it will be actually not very visible electromagnetically, this whole thing happening, the falling of the stuff happening. Okay, so that's what's going on. And I believe that if you want to Do you believe there is a singularity in black hole? Well, I mean, classically, yes. Classical physics says that there is a singularity. Classical physics says that there is singularity in a black hole and also singularity in the Big Bang. The Big Bang is a singularity and black hole is a singularity. I don't know anything more about. I don't know. I don't. I don't have a deeper insight about singularities, if that's what you're asking. Hi, Gladys. Gladys, how are you? Hi, XNT. I can't. I couldn't keep up with all the comments. UFO disclosure for peace on Earth. I'm not sure about this neutron star and white dwarf thing that you're saying, Jason. As far as I know, the white dwarf, neutron star, black holes, they're not the same thing. So the lower mass stars, stars that have like around 1.5 solar mass, will die to become a white dwarf. More massive stars become neutron star. The most massive stars become black holes when they die as the stellar remnant. So in that sense, black hole is a stellar remnant example. In other sense, as in black hole after lots of accretion onto it, becoming bigger and bigger, like the supermassive black hole at the center of our own galaxy, is a more than just a regular black hole. It is, that's why it's called a supermassive black hole. It has done a lot of eating of matter. Gladys says good. Australian. Welcome, Australia. How are you doing? XNT. Thank you, XNT. I have much to learn from you in time. Thank you. Just buy the books, XNT. It is true. There is links to the books in my channel. You can buy the books or you can not buy the books, up to you. Coming to this discussion, is obviously optional. So you can come if you find some value. If you don't find value, then I'm certainly not making you come to this discussion. So up to you. It's completely optional. But basically, I'm here learning physics with you guys as well. And I did learn it uh, to some extent in the past, and I continue to remind myself. And the books do certainly help a lot. And also, it's like when I was actually in school, I didn't have time to read all of the books on astronomy, astrophysics, all of the little details, right? So now that I talk about these topics, I actually end up learning more. So um, I do appreciate the books a lot and the authors of all the books. Do you believe black hole have closed time-like curve? That is true, right? Do I believe black hole has closed time-like curve? I mean, is that the same as saying that the light does not escape a black hole? She is teaching me a lot. Thank you, XNT. Teachers do use books. So there is that. Okay, so 18.6, or no, 18.3. This was also very interesting. I loved this section of the book. So by the way, this book is called, I'm gonna link to this book, Foundations of Astrophysics. Barbara Ryden, Bradley, and Peterson are the authors of this book. I will absolutely link it again to the live, but in this little part of the book, let me just confirm for you. So it was very, oh, here it is. Black hole. Do you know if Andromeda have any rocky planets? I don't know, actually. I know we've discovered some exoplanets. They're actually more. We actually also have a live on exoplanets, by the way. So we have a few lives on exoplanets because that's a big topic as well. But the exoplanet lives, or the exoplanet research that has been done so far, mainly shows that we have found planets that are more like Jupiter's or Neptune's than they are like Earth, or I guess rocky planets, like somebody is asking. So I'm not sure if there are rocky planets in Andromeda. Maybe, I don't know. So general relativity predicts the existence of singularities within event horizon. So this is the black hole singularity thing. That the fact that the gravitational field becomes so high for a black hole, leading to basically a singularity. That's what this is, right? This is the classical thought about a black hole, is that there is a singularity within it. A singularity is a point of infinite density and infinite space-time curvature. So infinite density, infinite space-time curvature, in other words, that infinite gravitational field thing, right? So it's like general relativity is as a theory of gravitation, right? Where gravitation is the bending of space-time. So imagine something with so much gravitation where it's almost like it creates this point of infinite density, infinite curving of space-time, and that is a black hole, according to general theory of relativity. Now, is general relativity very happy about this singularity? Not really, but that's sort of the math of it, okay? So, however, to test the predictions of general relativity and see whether singularities really exist, you would have to enter the event horizon of a black hole. So this is where we were talking. I was mentioning how the book gives an example of somebody diving into the black hole. So we'll see. Presumably, once there, you'd be able to discover the answer, but you wouldn't be able to communicate your results to the outside world. It would be the ultimate scientific tragedy, having a great result, but being unable to publish it. Lurid sci-fi movies sometimes regard black holes as dangerous vacuum cleaners, sucking up everything within reach. In fact, when you're far outside the Schwarzschild radius of a black hole, its gravitational pull is just the same as you'd feel from any other object of the same mass. So it's not that bad in the sense of like what happens around the black hole. It just, everybody experiences the gravitation of the black hole, like you would for any other mass of the same mass as the black hole. What makes black holes potentially dangerous is their extremely compact nature. As you approach the central singularity of a black hole, you feel stronger and stronger tidal forces. So this is related to the spaghettification that somebody asked about. Until you're eventually ripped apart. If you want to spare your friends and relatives the gory sight of your demise, you should take care to dive toward a high mass black hole rather than a low mass black hole. For a low mass black hole, you will be ripped apart before entering the event horizon. For a high mass black hole, you would be ripped apart after entering the event horizon. And then there's the math for why. So this is the part that I really love about this book. It says that because, so like maybe your friends and relatives are waiting a little farther away to see what happens to you. Hopefully they don't wish you to do this, but basically, if you dive towards a low mass black hole, you'll get ripped apart before the event horizon, which means that your friends and family will see you getting shredded. But if you dive into a higher mass black hole, then you will be ripped still, but inside the event horizon, and nobody will have to see you get shredded. So that's the recommendation. Eversor said something. I don't know what he said. Did he or she say? Rockets are so 1947. Okay. Was there a question? Is that what this is? You can safely apply the Copernican principle to most questions, which means the things we know and experience are not unusual. So if we have rocky planets in the Milky Way, then Andromeda will. Right. But having said that, so somebody pointed this out, but we haven't found too many when we look for exoplanets, partly because maybe a lot because the techniques associated with finding exoplanets are biased towards finding hotter and bigger planets like Jupiter's and Neptune size or whatnot planets. But what we have found so far are more planets that kind of resemble Jupiter's and Neptune's. But the interesting thing is that we find them at distances that are closer to their host star. So what we've found when we have gone to look for exoplanets, so I kind of gave you the observational answer. So sort of the theoretical answer might be yes, of course, we have rocky planets here in the Milky Way, in our own galaxy. So why not in other galaxies too? So that's kind of a philosophical answer, right? The philosophical answer is, oh, we philosophize that we are not special. So there are rocky planets in other galaxies as well. That is one answer. The other answer is the observational answer. What have we observed so far? Have we seen a lot of Earth-like planets? And the answer is no. What we see is more of the hot Jupiters and hot Neptune type of planets when we observe. Now, that could be because of our observational techniques being biased towards those planets. It could very well be, but that's the observational answer, okay? She don't care about you or your suggestions. You won't feel anything. Is that like, I don't know what that means. Space-time is warped by a rotating black hole, closed time-like curve. Potential for back. Oh! Space-time is warped by a rotating black hole. When did we talk about rotating black holes? We did. Space-time is warped by a rotating black hole, closed time-like curve. Closed time-like curve. Potential for backward time travel. Do you believe? Sure. If it's possible physically, um, a rotating black hole, closed time-like curve. This is all coming back to me. We did talk about this at one point. Potential for backward time travel. Sure, sure. Actually, we know that time travel is basically possible microscopically. So if it's possible microscopically, actually, I'm willing to believe that time travel is extremely possible. I mean, it is possible for particles, for microscopic level stuff. But macroscopically, can we experience time travel and go backwards in time? I'm not so sure. I would maybe say no. Anything else? We kind of talked about, let's see. We kind of talked about the ripping of space-time. I love that there is so much active participation by people. Thank you so much, everybody. And I'll link the book. And thank you so much for the questions, Drew Crew. And I think there were at least a few other people who were asking. So thank you so much. Will we ever harness the power of the sun? Don't we already, to a large extent? Or do you mean the nuclear power of the sun? Yes, on tearing space-time. How could you go about this? Yes, tearing space-time. How could you go about this? What do you mean? Or are you asking? There is more on that topic that I didn't get to today. Yeah. Are you asking how to tear space-time? So basically, we said that the tearing of space-time in classical is not allowed. In general relativity is not allowed, but maybe in quantum or in string theory it could be allowed. Ah, yeah, you're asking, how could you tear space-time? We didn't get to it. Blue energy is basically a time machine. Asking for a friend. What are you asking? I'm gonna rename this. Um, ISRO, the Indian Space Research. Oh, can you do a super chat? That would be lovely. Keep the smart questions rolling, guys. Who is your favorite person in the chat and why is it Drew? Why is it Drew? Drew seems nice. He or she asks, or they ask pretty good questions. Madhura Sagar, hi. You are right if it's not proven. Okay. Thank you, XNT. You're very nice. Thank you. For a second, Madhura Sagar, I thought you were a woman, but from your comment, I can tell you're a man, and a very rude one, that too. So get out, please. I guess none of my mods are here today. It's quite a sad day for me. Okay, Merton can bend space and time. So, um, even though I didn't get to everybody in the chat and I didn't get to all the questions and comments, hopefully I covered some stuff. And Drew Crew does seem very nice. And XMT as well. Thank you. Yes, correct. See, what a nice comment. We basically don't know what dark matter is, but we only observe it gravitationally. Exactly. We don't know what dark matter is. We don't know the particle nature of dark matter, but we do observe it gravitationally. We have direct evidence of it gravitationally, such as with the velocity curves that I was mentioning um, with our own galaxy, things moving and orbiting our galactic center, and the velocities of those things associated with that. So, by the way, Jason, if you're interested in understanding how dark matter fits into the cosmological picture, we have certain cosmology lives called some things like cosmic ingredients, et cetera, et cetera. I have a few lives that are sort of more cosmology flavored. And in those lives, we have talked about the cosmic ingredients, by the way, which I am feeling tempted to say right now. The cosmic ingredients. So, somebody mentioned about the universe. Uh, Jason mentioned about the universe and what is natural to it. I would say dark matter is a natural part of our universe. It's a very important part of our universe. We just don't understand it very well yet, but that doesn't mean that it is outside of our universe. Okay. Um, no. So cosmic ingredients include photons, baryons, neutrinos, dark matter, and dark energy. So those are the 5 cosmic ingredients. So if we are considering cosmology as a whole, the universe as a whole, and cosmologically what makes up the universe, then those are the 5 things. It's going to be photons, so that's light, neutrinos, that's a lepton, baryons, that's neutrons and protons, dark matter and dark energy. So we actually talk about this in detail in some of our lives in the past. And these lives may be called something like cosmic ingredients or cosmology something something. Hopefully you find them and see about dark matter in those lives, okay? We mostly see dark matter around galaxies. In the halo, yes, there is dark matter in the halo of our galaxy and other galaxies. Yes, very good. Very good, Drew Crew. There's a few very good students of astronomy and physics here. I don't know what happened to my eye. Under my eye, there's something, like a bump under my eye. Okay, rename this. I'm renaming the live. I feel like I have a bunch of bros in the chat. How did I end up with you guys? Oh, interesting. It really acts almost opposite to other actions. It seems foreign. I think it comes from outside. So I see. So it's definitely part of our universe. That's where I was making the comment earlier of the cosmic ingredients. But as far as the origin of dark matter, you are saying that dark matter could be from another universe, as in maybe something is happening in a different universe and dark matter is a manifestation of that in our universe. That honestly, we did talk about that a little bit. At one point, we did talk about how there could be something going on in another universe. Now, this is just an idea, okay? There could be something going on in another universe, and the effect of that on ours is dark matter. If this is the sort of thing that you're suggesting, Jason, then we did actually mention that as well at one point. Indeed, but I thought you were saying that dark matter is not part of our universe, and I'm just saying that it is, as in we see the direct evidence of dark matter in our own galaxy, even, and other galaxies. And so it's definitely part of our universe in that sense, and it's definitely a cosmic ingredient. It's one of the uh, main things that contribute to the energy density of the universe and such. But as far as why dark matter is even a thing and where from it comes and what it really is. I mean, actually, another way to research it would be to figure out where. So the smooth universe and the overdensities in the smooth universe that lead to the galaxies and the stars and all that. So dark matter, there is something to do with dark matter with that too, probably. And I'm not 100% sure, but it would be a good thing to probe is where in those over densities did we get dark matter, or is dark matter coming from some other effect, or is it the effect of a different universe on us? I don't know, but it's an interesting thought for sure. To not fall apart from their rotation. Oh, it's kind of like being held together, you mean? Does dark matter come in entangled pairs? Does dark matter come in entangled pairs? Entangled pairs. Entangled as in we have a pair, we have a part of the pair and another universe has another pair, you mean? Or so I don't know. So this idea, it's a very interesting one that somebody said, which is that didn't we talk about oh my gosh, I'm forgetting where we saw this. Um I'm forgetting the exact context of where we saw this, but basically it involved an explanation or an idea. Again, it's not possible to, or it might be possible, I don't know, but it's not proven or anything. But the idea was that there was something going on in a different universe, and we are sort of seeing an interaction of that in this universe, and the way it manifests is dark matter. So if that's what you mean with the entangled pair thing, maybe, but I don't know. Certainly, I don't know about this. And it's an active area of research as to what dark matter really is. It's named dark matter because we don't see it with light. It doesn't interact with electromagnetic waves. It doesn't interact with light, and we cannot see it. It's not visible to us in that sense. We only feel it, and we observe it gravitationally, but we don't see it in other ways, in other electromagnetic waves. So that's why it's called dark matter, but also it's mysterious. It's full of mystery is the other thing, is why it's dark matter. Quantum entanglement. Ah, I don't know. I don't know enough about dark matter and its particle nature. And indeed, I don't know if that is known yet, to the point of being able to say if there is quantum entangled pairs of dark matter. I mean, why? Yeah, I mean, maybe. I don't know. I don't know enough about the particle nature of dark matter to say whether there is a entangled pair. But if supersymmetry, I mean, if all the particles have super partners, I mean, could dark matter kind of have anything to do with supersymmetry? That would be another question. Or is that something I wonder if we've probed it that way. Basically, all the particles, according to supersymmetry, have a super partner particle, right? A SUSY partner particle. And I don't know if dark matter has anything to do with that, a SUSY partner particle. You know what I mean? So, I mean, yeah, I don't know. I don't know if the particle, I don't know what the particle nature of dark matter is. So I can't say really if there is a partner particle or not. Do you believe the Earth is flat? No, the Earth is in fact not flat. Israel. Okay. Galaxies spin too fast for general relativity so Drew Crew. My favorite, Drew Crew, is saying galaxies spin too fast for general relativity to explain why it stayed together. Why that scientists think it dark matter that keep them together. Okay. I mean, dark matter does have interesting. This is very true. Uh, that dark matter, whatever it is, we don't know exactly what it is, but it has a very important role in the universe, right? It has a very important role in this galaxy stuff, in large scale structure formation, in the galaxy formations, keeping the galaxies together, all that stuff, blah, blah, blah. Lots of very important things that dark matter does. So, of course, understanding dark matter is always very good. It's very relevant. It has an important role. So, thank you for sharing that. It would be, as I like to say it, it's one of the top three questions. The top three questions are: what is dark energy? What is dark matter? And what is the origin of all the elements? We know how some of the elements are made, of course, but there are some heavier ones that we don't fully understand how they're made. So in my mind, the top three questions are: what is dark energy? What is dark matter? What is the origin of all the elements? And those are the top three questions of the universe. So very important to understand what is dark matter. Yes, the supersymmetry, it's curious. Yeah, so I wonder if it's like a SUSY particle, um, and it would, I mean, if it could, it's like two birds, one stone, or I don't know how many birds, multiple birds, one stone type of thing would be if the thing that makes string theory work, which of course you need supersymmetry, and also the thing that unifies the non-gravitational forces. For that too, I believe you need supersymmetry. And then supersymmetry just kind of cleans everything up nicely, right? But supersymmetry partner particles are not known yet. And so they're probably kind of elusive. They're probably kind of hard. It would be kind of nice if dark matter was had something to do with Susie, with supersymmetry, and then maybe all of these questions could be answered at the same time, and some of the theories or some of the things that heavily depend on supersymmetry would be benefited from it. If those things are correct, that is. I don't know. I don't know. The theories that need supersymmetry, of course, are trying to explain something bigger. So, hmm. Hi, Sama. Would you ever own a dog? Um, yeah, actually, when I was a child, I really wanted a dog. My grandmother had a dog, but I always wanted one. Thank you. I'm creative writer. Magnets. Oh, wow. Oh gosh. Dark matter is the main source by which all matter particles come. No, 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 no. Dark matter. Dark matter is the main. Dark matter. No, 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 no. Dark matter is a type of matter, and it is the main component of the matter density in the universe. In other words, there is much more dark matter than there is ordinary matter. But I am not sure that ordinary matter comes from dark matter. Ordinary matter, as far as we know, is made up of leptons, quarks, you know, that type of stuff. So it is not dark matter. So no, no, no. I would say dark matter contributes to the matter density more than ordinary matter, or dark matter is an important component of the overall total energy density in the universe, which includes all matter, dark energy, everything, right? But ordinary matter isn't dark matter just no, 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 no. Antimatter is not dark matter. Antimatter is just ordinary. Antiparticles like the positron is just an ordinary particle, not dark matter. Nope. No, 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 no. No, 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 no. Right, right. Correct. There is more dark matter by mass than ordinary matter. So that is what I meant with the energy density having more contribution from dark matter than ordinary matter. But antimatter, an example would be the positron, which is the antiparticle of the electron. That is ordinary. That is not dark matter. Did you work on neutrinos in Antarctica? Yes. Is dark chocolate considered dark matter? Dark chocolate is considered ordinary matter. Dark chocolate is just ordinary matter. It's just mainly baryons. Baryons are protons and neutrons. Same thing that makes us, same thing that makes the dark chocolate. Baryons are 5% of the energy density. Dark matter is 25%. So there is more dark matter than ordinary matter. That's what we mean. There's like 70% dark energy, 25% dark matter, 5% ordinary matter. So by those percentages, there's more dark matter than ordinary matter. And then most of it is dark energy. That's sort of the cosmic makeup at this current stage of the universe. So dark chocolate is baryons, which falls into the 5% of the cosmic ingredient of the universe. Okay, good question. And antiparticles are less than particles. There's more matter than there's antimatter. By the way, we were reading about this from the other book called Atom by Dr. Lawrence Krauss. So we can go back to that next time. But basically, there's more matter in the universe than antimatter. There are more processes that make matter than there are for making antimatter. But for example, you could do experiments that would produce the positron, which is the antiparticle of the electron, right? And that is still part of the standard model of particle physics, which currently does not explain dark matter, okay? So antiparticles are not dark matter, okay? We actually talked about matter, dark matter, antimatter, and superpartner particles. So particles, we know what they are. Particles are leptons, quarks, and bosons, examples of which are electrons, up and down quarks, which make up the neutrons and protons that we know and love, and photons, which are bosons. So particles are just leptons, quarks, and bosons. Antiparticles are sort of the anti-particle partner of these particles. Dark matter is this other thing which makes up most of the matter in the universe, but it's dark, does not interact with light, but does interact with gravitation, and it's an active area of research. Superpartner particles are theoretical supersymmetry, superpartner particles of all the particles that we know that are yet undiscovered, as far as I know. All different things, okay? Dark matter is not just antimatter, okay? I have bigger biceps than you. Than me? Okay. I hope so. I'm working on mine. I lift I bench 20 on each side. 20 pounds on each side. 20 pounds of baryons on each side is what I bench. So I do hope that your biceps are bigger. If the multiverse theory is true, there must be a universe where this theory isn't working. What's your thought on this? Multiverse theories. There must be a universe in which this theory isn't working. Which theory? Thank you for being here, everybody. Welcome to the live, and please rewind to see the full discussion. Please rewind because we talked about Brian Greene's book, The Elegant Universe. We talked a little bit about the tearing of the fabric of space-time and a little bit about wormholes. That also led us to black holes. So then we talked about black holes, and now we're kind of looking at questions and answering them and stuff like that. We also don't know. Okay. We don't know what consciousness is. Okay. Thank you for liking, by the way. Thank you for liking the live. Thank you for liking and subscribing, everybody. Well, let me go on the laptop. I'm missing some of the people's comments are going by and I'm not always catching them. It's hard to see on the phone where I'm recording. Ah, oh, I love this question. Do you think neutrinos have anything to do with dark matter since they're hard to detect? Hi, anime. I don't know about that. I don't know if ETA Coronae will collapse into a black hole. I'm not sure. I don't know about that one. But I love this question. So, did you know, Drew Crew, my favorite, that neutrinos were considered a dark matter candidate? Were you here during my dark matter candidate live? Guys, are you ready for this? There were three dark matter candidates. They were all sort of what do you call it, dismissed, or some of them are still being researched. But the first dark matter candidate was actually the neutrino. Neutrinos are extremely elusive leptons that are weakly interacting only and also don't interact with electromagnetism. So neutrinos were absolutely very much considered as a candidate for dark matter. But then they were not thought to have enough mass really to account for all of the mass or all of the extra mass that we see in our own galaxy from dark matter. So, good guess. I would say neutrinos are probably a very good guess as to could this be dark matter. But unfortunatamente, neutrinos were not thought to be able to account for all the mass that we see for dark matter. Okay, so probably not, but I love it. Neutrinos are so very elusive indeed. Some of the most elusive, but also very pure cosmic messenger because of that exact reason, because neutrinos don't interact with much on the way to us from some astrophysical source, is why we, for example, picked neutrinos as a cosmic messenger, an astroparticle or astrophysical messenger particle. Um, they interact weakly, but they don't, and they interact gravitationally. They have some mass, but very little. At first, neutrinos, we didn't even know their mass. We thought they could be massless, etc. Lots of mystery with the neutrino. But they do have a little bit of mass. And at this point, when now we think at the current, I believe, I mean, I could be wrong because dark matter is an active area of research. So things could change day to day. But I don't think that neutrinos account for the mass that is missing, which would have to be accounted by dark matter. Okay. But let me tell you about the other. Okay. So did you know that weakly interacting massive particles, WIMP is a dark matter candidate, sort of is inspired by neutrinos. So it's the thought was like, okay, so neutrinos don't do it. So maybe there's, let's imagine or think up a particle, which is kind of like the neutrino, but has more mass. It's kind of like you thought the neutrino might be dark matter. Then you're like, oh, shoot, not enough mass here. So let's think up WIMPs, which is the weakly interacting massive particle. Very much like the neutrino, but more mass. So that is still, I believe, a dark matter candidate. So we will see if the WIMP of some kind ends up being dark matter. Then there's a group of people who also then considered another type of candidate for dark matter, which was called machos, sort of as a opposite to the WIMPs. And this was massive massive compact halo objects. That's what macho stands for, massive compact halo objects. So then they thought, okay, what if they're not anything too unusual, but just some more massive compact halo objects that are so cold or brown or kind of like a white dwarf, but not white, not luminous, non-luminous massive compact halo objects. Could those be accounting for dark matter? Unfortunately for this one too, if there were such machos, such compact halo objects, we would kind of see them with gravitational lensing, and we don't see enough of them also to account for dark matter. So a lot of these candidates kind of are not considered. Here's Baji, by the way, are not considered really viable for the explanation of the dark matter that we see in our own galaxy and elsewhere. Okay, but WIMPs Maybe. Maybe it's somehow there's a cousin of the neutrino that is more massive that we simply have not found yet. Maybe it's a SUSY particle. Maybe it's a, I don't know, some other kind of particle that we just haven't learned about yet or found it. I mean, I guess technically it's been found in the sense of the dark matter signatures or dark matter evidence that we have, but we haven't found it in a particle physics lab, um, which gives us the particle nature of it. Hi, Samo. Neutrinos are. Hi, Samudrala, Girish, Maruthi, how are you? And petting Baji as we speak. Beginning of matter formation to energy. Oh, Baji is stealing this. Oh my gosh. Wimps. I don't know what you mean by hence the area created to all subatomic. Not sure what that means, Jason. But WIMP is a dark matter candidate as well. What do you think of tachyon? I don't know if I have strong feelings. Why don't you live in Twitch? It's better platform. All you need is yourself. Very nice. Some of these questions are quite are very interesting. Good to know what you guys are interested in. Somebody said tachyon, and then Higgs field. So you really like the Higgs field. We have to talk about that sometime. I'll make a note of it. Higgs field and tachyons that we didn't get to today. Stop taking the What does that even mean? Robert Higgins. Oh, where do neutrinos come from? Wow. Baji. Baji's fur is like flying into my face. So actually, do I have a pen here? Let me write that down. That people want to know about. I before I forget, let me write down Higgs field. They want to know tachyons. Anything else that I didn't cover today? Oh, where do neutrinos come from? This is cool. We will just go over. Actually, that's a great point. We will go over the Big Bang nucleosynthesis you know, the in the Big Bang, during the Big Bang, um, during the Big Bang, we basically during the hot Big Bang cosmic soup, we basically just had mostly photons. Did I say photons? Yeah, photons, electrons, positrons was the main cosmic soup in that radiation dominated early universe. Do you were you here for our cosmology type of lives where we talked about the evolution of the universe, where it used to be radiation dominated in the beginning, and then neutrinos had a bit of a breakup with the hot soup at that point. Actually, it's almost like I think it's probably that at one point the universe was this soup of the energy regimes were that are split up now between electromagnetism, strong nuclear force, and weak nuclear force may have been unified back then. But at one point, anyway, there's one, that's one thing. And neutrino, I mentioned about that because neutrinos interact with the weak nuclear force, right? But at one point, they might have separated because the thing that was keeping them in sort of a equilibrium with the cosmic soup that did not keep up with the expansion of the universe, so the neutrinos kind of separated out of that. So anyways, in short, neutrinos separated out, but we can talk about it more next time. Where do neutrinos come from? I know where neutrinos come from. Okay, go ahead. Why don't you live in Twitch? I guess I could live in Twitch. Western Dike energy? No, I'm new to your video lives. Okay, well, Drew Crew, we have talked about cosmology quite a bit a while ago. I mean, it might have been, some of it was recent, some of it was a while ago, months ago. And there were some interesting discussions about the Big Bang nucleosynthesis, cosmology, cosmic ingredients that you might like very much. I hope you see it coming up on your feed, or you can go find it under the live tab of my channel. Did I say that right? Yes, please do find it under the live tab of my channel. I think there's a lot more that you might like. He is saying you're very feminine. Oh, okay. Thank you, I guess. I think that's a compliment. I don't know. Higgs field, they want to know. Tachyons, they want to know. And where do neutrinos come from? Okay. I'm gonna name this How to Dive into a Black Hole. Astrophysics, astronomy, black hole. Tearing of the fate, Riemannian atoms. Trying to organize my stuff a little better. So are you guys are you guys the type to stay up really late on Monday? Do you also stay up late on Tuesday, Wednesday, Thursday? Are there some days that you go to bed early? If you're from the US, that is, or from North America. Um, I guess, yeah. Shouldn't make any assumptions. In North America, it's getting a little late. Oh, welcome to Africa. Oh my gosh. Sama Uzumaki. Oh, I love that. Sama Uzumaki. Uzumaki. I'm in Africa. Oh, that's lovely. Welcome, Africa. I usually start like this. Welcome, Africa. Welcome, Asia. Welcome, Europe, North America, South America, Antarctica, Australia, New Zealand, Madagascar. Where in Africa? If you want to share. If you don't, that's fine too. What exactly did you do in Antarctica? Oh my gosh. Well, that's a whole nother life. Maybe I can talk about that tomorrow. Thank you. Good night, XNT. Thank you so much for being here. Really appreciate it. Lovely to have you. Lovely to see you in the live. XNT. 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 I love that name. It's with an X, N, and the T. Xed. Accent. XNT. Accent. Accent? XNT. I like the XNT. What exactly did you do in Antarctica? Well, I worked on, how do I put it? I worked on assembling, testing, getting ready, launching and deploying a mission that looks for neutrinos in the Antarctic ice via RF techniques, utilizing radio antennas that we hang from a gigantic balloon in the sky that orbits Antarctica, utilizing the polar vortex. And so when the weather is ready, when the polar vortex gets ready, is hopefully when our mission would be ready. And I was one of the lead grad students on that mission who was getting everything ready and tested and put together and assembled and I don't know, all of the things. Um, the part I did not do is to put helium in the balloon. NASA does that. I wasn't allowed to touch the balloon. NASA puts helium in the balloon and gets it ready for the hanging part of our detector. But getting the detector ready and getting the our instrument, detector, sensor, everything, all that ready um, just before the balloon gets attached to it to then launch it. And then, oh, I also did all of the post mission stuff, telemetry, monitoring, doing stuff, sending signals to the satellite, which talks to the balloon mission if it needs any changes and things like that. All of that as well. But I was not in charge of the balloon. That's the only part that we don't do. She was stopping an alien from taking over the Earth. I did hear about this movie. They watch it down in Antarctica, actually, I believe. Yeah. Also, I ate a lot of food. Good food there. The best chefs. Ooh, North Africa, Algeria. That means I'm white. Oh, Algeria. Okay. Okay, good to know. I had to think about that. But good to know. Thank you so much for being here from Algeria. Discuss. Okay. Tomorrow I have to do some box openings. I don't know if they were leopard seals or not, but yeah, I saw a lot of seals. There were some really nice, uh, really big seals, mommy seals and baby seals. Brazil, are you from Brazil? Jolmer Alves. Joel, Hol, Joel, Jolmer Alves. Brazil, Brazil, Brazil. Love it. Welcome to Brazil. Welcome, Eversor. Sazetta reticuli. Not sure what that means, but hello. Okay, thank you so much, everybody, for being here. Thank you for the hearts. Thank you for all the emojis and comments and everything like that. Really, really appreciate everybody for joining tonight and discussing and commenting and putting your thoughts in the chat. I should get going, I have to get some sleep. And good night, good morning, good afternoon. Thank you for your support. Where is my usual crowd of people? Where is my usual crowd of people? I don't see any of the older people. Say bye, guys. Say bye. Bye. Bye, bye, bye. And yeah, thank you. Please do like, share, subscribe. And if you want to do a super chat, you should do it now. Let me get a water. I'm always here. Oh, thank you. Appreciate your help. Thank you guys. Tough crowd. No super chats. Only pseudo mean or a few nice comments. Steven, yeah. Steven is a good friend. That's for sure. On these lives, that is. I know him through the lives. Thank you. Mm, that's right. Acacio was here. And he's very supportive, yeah. Ah, he must have gone to bed. Mm. All right, guys, bye. Good night. Have a good sleep and